In the previous lecture we have derived the Berge-Vitta method for the solution of the polynomial equations. We have shown how we can extract a simple root from the polynomial equation, deflate the polynomial and then obtain the next root if it is required. Now let us just take one more example on this to just illustrate what would we should do if a coefficient is missing in the given equation. So let us start with an example, and the example which I will take is as follows. Now I want to find a negative root of the equation a negative root of this equation 3x to the power of 4 plus 5x cubed plus 6x plus 10 is equal to 0 is near minus 1.9. Now find this root. Using, let us take two iterations of Berge-Vitta method. And also let us find the deflated polynomial. Find the deflated polynomial. Here we are already given the negative root, that the root is near minus 1.9. So we are given the initial approximation as minus 1.9, and we want to use the Berge-Vitta method, two iterations, and then find the deflated polynomial also. So we can see here that in this polynomial that is given to us, the one factor is missing, that is x square is missing here. So I just want to illustrate how we are going to include this particular term. As mentioned, we shall use the coefficient as 0 in the Berge-Vitta method. So we shall therefore write the coefficients of this as 3, 5, 0, 6 and 10. Then we are applying the Berge-Vitta method with respect to the initial approximation 1.9. Therefore B naught is A naught, therefore I will have 3, multiply these two, I will get minus 5.7. So I will have here minus 0.7. Then I multiply 0.7 into 1.9, both are positive sign, I will get here 1.33. Add these two, I will get 1.33. Multiply these minus 1.9 and 1.33, I would get here minus 2.527. Subtract it, I will get 3.473. Then again multiply this 3.473 is minus 1.9, that gives you minus 6.5987. So this value is 3.4013, which is the value of B4. Then I repeat one more step here. So I would get 3 and I will get minus 5.7. I add up, I will get minus 6.4, multiply with minus 1.29, I would get 12.16. Add this 13.49, multiply by minus 1.9, so I will get minus 25.631, which gives me minus 22.158, and this is equal to C3. This is your C naught, C1, C2, C3. So this is our coefficient C3. Now we have completed the synthetic division. So let us use the Newton-Raphson method. There is P1 is equal to P naught minus B4 upon C3. So that will be P naught is minus 1.9, I have minus B4 3.4013 divided by minus 22.158, and I get this value as minus 1.7465. So the first iteration has given the root as minus 1.7465. Now I would continue the synthetic division, the second iteration using minus 1.765. Now the remaining part is trivial, therefore I will leave this to complete for you, but I will give the solution of this problem what you should have. So the second value is P2 comes out to be minus 1.6810. We have been asked to perform only 2 iterations. So we shall stop the iteration at this particular level and then find the deflated polynomial with respect to this. So I now perform the first step of the synthetic division procedure, wherein I will get the q2x, I will give the answer for q2x comes out to be 3x cubed minus 0.043 x squared plus 0.0723 x plus 5.7885. This is the deflated polynomial, and I would also give the exact solution for this problem. We have performed only 2 iterations, therefore we have not yet reached the required accuracy. The exact value is 1.666, and the deflated polynomial q2, the exact value is 3x cubed plus 6, 3x cubed plus 6. Therefore you can see that the root, we have only got only one decimal place, we still need at least 2 more iterations to get the few more places accuracy, and these 2 values would then go to 0. Therefore the idea here is to apply the Newton-Raphson method to a polynomial equation, so that we can extract a simple root from that particular equation. The modification for this will be for multiple root can be done. We know if the methods we have given earlier for multiple roots, the same can be applied, and we can apply the Newton-Raphson method for a multiple root also. Now we would go to the method known as the Bairstow method. The Bairstow method is that wherein we will extract a quadratic factor and not a simple factor. So we can say we extract a quadratic factor x squared plus px plus q from the given polynomial. So let us take the polynomial, let us write it again, a naught x to the power of n, a1 x to the power of n minus 1 plus so on a n minus 1 of x plus a n. Now if you extract this quadratic factor, then this can give us a complex pair of roots, or it can give a real pair of roots. So we are extracting a pair of real roots or a complex pair. So we would then have a complex pair or a pair of real roots. Now if we divide p n x by x square plus px plus q, if this was exact, I would get a polynomial of degree n minus 2. If it is not exact, then I will have a remainder. So let us take that, let x squared plus px plus q be not an exact factor. Now if it is not an exact factor, then the division by x square plus px plus q would give us a polynomial of degree n minus 2, and the remainder because we are dividing by quadratic, the remainder will be a linear polynomial. Therefore I can write down p n x as x squared plus px plus q, which is the quadratic factor that we want to extract, into a polynomial of degree n minus 2 x plus a linear polynomial will be the remainder. So it will be of the form some r x plus s, where q n minus 2 is a polynomial of degree n minus 2. So I can write this as some b naught x to the power of n minus 2, b1 x to the power of n minus 3 plus so on b n minus 3 x plus b n minus 2. So, it is a polynomial of degree n minus 2. So, it will have the coefficients as b naught x to the power of n minus 2, b 1 x to the power of n minus 3, and the constant term is b n minus 2. Now, p and q are the initial approximations to the exact values of p and q. Therefore, as the iteration goes on, the values of p and q change, therefore, the values of the remainder also changes. In other words, r and s there will be functions of p and q. Therefore, r is a function of p q and s is also a function of p and q. Now, as p and q is varying, this r and s is varying, therefore, they are nothing but nonlinear equations of p and q. So, these give you two nonlinear equations. They are two nonlinear equations in the two variables p and q. Now, we would be getting the exact factor if r and s were identically 0. If r and s were identically 0, this is exactly divisible and we have got the exact factor. Therefore, the problem is to determine p and q such that r and s tend to 0. Now, therefore, if p and q tend to exact values, if p and q tend to exact values, r and s tend to 0. That is because the remainder should be equal to 0. In other words, the problem, if you look back at this, it is to find p and q, such that r of p q is equal to 0, s of p q is equal to 0. But we have discussed this problem already earlier. This is a system of two nonlinear equations in two variables p and q. We have discussed the solution of the n nonlinear equations in n variables. So, we shall just apply it for the case of two variables and find out what will be the values of p and q from here. Now, let us denote the partial derivatives by simple notation, so that it is easy for us to write down the solution for this. So, let us denote the partial derivative of r with respect to p. We are talking a function of two variables, therefore, we shall be talking of the partial derivatives of r and s. Let us just denote this by r suffix b, delta r upon delta q by r suffix q. Similarly, this is delta s upon delta p is equal to f suffix p, delta s upon delta q is s suffix q. We just denoted the partial derivatives by simple notation using the suffix for the. Now, we know that if I am solving this system of two equations, what we have to solve is the Jacobian into the increment is equal to the right hand side evaluated at all these points. The Jacobian of r is delta r upon delta p is the first element, the second element is delta r upon delta q. So, what I will have here is r suffix p, r suffix q, s suffix p, s q. So, these are the four partial derivatives that appear in the Jacobian, and these are the increments that we are solving for. So, I will have here h1, h2 as the increments. On the right hand side, we have the r and s evaluated at the particular iteration. Let us put the iteration as k now here. So, this will be r k and s k. So, this is the Jacobian, this is the increment, the right hand side with opposite sign. Now, since it is a 2 by 2 matrix, find out the inverse and then write down the what will be h1 h2. So, let us write down what is our h1 h2. This is equal to, if this minus sign, let us put it in the numerator. The determinant of the coefficient is r p into s q minus derivative with respect to q of r into s p. So, let us write down the denominator first, r this minus s p r q. So, that is the determinant of the coefficient. Now let us write down its cofactors. So this is SQ, the cofactor of this is RP, then cofactor of this is minus SP, and then let us take the transpose also. So I will have minus S suffix P minus R suffix Q. So this is the inverse of this 2 by 2 matrix, and this is multiplied by R and S, all evaluated at K, all the terms are evaluated at Pk Qk. So all the terms we are evaluating at Pk and Qk. Now let us write down one more step from here, so that we have it as this. So let us simplify it and write the one more step, H1 H2 will be equal to, let us multiply it out. This is, I will keep the denominator as it is, now I will multiplying this, therefore R into SQ minus S into RQ, that is the product of this first row and this vector R and S. Then the second one I will write this first one because of the sign that I have here, positive sign, minus R into SP. All the, as we have seen in the discussed earlier, all are evaluated at the current iterated value, that is Pk Qk. When once I determine this values of H1 H2, I have the next approximation. So the next approximation will be is equal to P1 is equal to, or Pk plus 1 is equal to Pk plus H1, Qk plus 1 is equal to Qk plus H2. So we are talking about the current iterate as a Pk Qk, therefore the next iteration will be Pk plus 1 and Qk plus 1, and have this particular result. This is the required result for our next iterate. Now I need to compute this. There are 6 quantities that are required, R, S and the 4 partial derivatives. So I need computation of R, I need computation of S, I need the 2 derivatives of R, and I need the 2 derivatives of S. So I need to evaluate 6 quantities at Pk Qk, and these 6 values I would like to obtain using the synthetic division. The synthetic division procedure that we have done for Birge-Vitta can be extended in the direct manner as we have done there for the extracting the quadratic factor also. I would start from here, we will write down P n x, that is your P n x, and let us start from here, is a naught x to the power of n, a1 x to the power of n minus 1, let us write down one more term, x minus x to the power of n minus 2, a n minus 1 of x plus a n, and this is your quadratic factor x squared plus p x plus q, and we are multiplying by q n minus 2, therefore b naught x to the power of n minus 2, b 1 x to the power of n minus 1, let us write down one more term, b x to the power of n minus 4 plus so on, plus b n minus 3 of x, b n minus 2 plus r x plus s. So this is our remainder. Now let us multiply the right hand side and collect the coefficients. So I will have here b naught x to the power of n, the product of x squared into this is the b naught x to the power of n, plus let us take x to the power of n minus 1, x squared into this product will give you x to the power of n minus 1. So I will have a b 1, and then the product of these two will give you x to the power of n minus 1. So I will have here b 1 plus p into b naught, that is coefficient of x to the power of n minus 1, Now I need next coefficient x to the power of n minus 2. So x squared will multiply this x to the power of n minus 2. So I will have a b2 here, then this px will multiply this to give me x to the power of n minus 2, that is p b1, then q will multiply this x to the power of n minus 2 to give me q b naught, x to the power of n minus 2. Now let us take the general term. The general term is x to the power of n minus k. So x squared will be multiplying bk x to the power of n minus k. So I will have bk over here, then p will multiply the previous term. The previous term is bk minus 1. So p into bk minus 1, and q will multiply the previous term, that is q bk minus 2 into x to the power of n minus k. Then let us come to the term x. Now when you come to the term x, I will have here x squared will not contribute because I need only x, therefore px into bn minus 2 it will contribute, that is p bn minus 2, these two will contribute, and then this will also contribute, that is q into bn minus 3. But we already have a r here, so we shall now add r here plus into x. Now the constant term, there is only one constant term here, q into b minus 2 and s over here. So I will have here q bn minus 2 plus s. Now let us compare the coefficients as we have done in the previous case. We will have here b naught is equal to a naught. So we will first have, let me put it here, I will have here b0 is equal to a0. I will write on this side again, b0 is equal to a0. Then I compare coefficient of x to the power of n minus 1, this is a1 and this is b1 plus pb1. So I will have here a1 is equal to b1 plus p times b naught. Now I solve for b1, b1 is equal to a1 minus p b naught. Now the contribution of all the terms has not yet come. Now if you compare x to the power of n minus 2, the contribution of all the three coefficients here would come into picture. So let us try the next coefficient is b2 plus p b1 plus q b naught, that is b2 plus p b1 plus q b naught is equal to a2. So I solve for b2, b2 is a2 minus p b1 minus q b0. So I have taken these two terms to the right hand side. Now let us go to the general term. The general term is left hand side is ak, the right hand side is bk plus p times bk minus 1, I am writing this term, plus q bk minus 2. So this will be my ak. Therefore the solution of this will be bk is equal to ak minus p bk minus 1 minus q bk minus 2. So we have solved for bk. Now let us compare the coefficient of x. The coefficient of x on the left hand side is a n minus 1. So the coefficient of x on the left hand side is a n minus 1, therefore from this I would get here a n minus 1 is, we will first write r, let us write r plus p times b n minus 2 q n minus 3. So I am writing from this term, that is r plus p b n minus 2 plus minus plus q b n minus 3. So let us now therefore solve for r, that is a n minus 1 minus p b n minus 2 minus q b n minus 3. And finally the constant coefficient is a n on the left hand side, and we have here this term Therefore, we will have a n is equal to q b n minus 2 plus s. Therefore, I solve it for s from here, s will be equal to a n minus q b n minus 2. Therefore, it is possible for me to generate the entire set of the equations from this particular generalized formula, wherein we define correctly what are the remaining values. So, let us write down the recurrence relation for the solution will be as follows. Will be simply b k is equal to a k minus p b k minus 1 minus q b minus 2. Now, we would like to use the k from 1, 2, 3, so on n. So, we will use this. Therefore, we have some quantities which are to be defined here. So, we know that b 0 is a 0. So, we will set where b 0 is a 0, that is from the coefficient. In order that we can write everything in terms of the recurrence, we will set b minus 1. When we put k is equal to 1 here, I have got b minus 1. So, b minus 1 is 0. So, that is how we define b 0 is a 0, b minus 1 is equal to this. Then we can also see, let us just look at this particular coefficient that we have written for r. The right hand side, if I set k is equal to n minus 1 here, a n minus 1 minus p b n minus 2 minus q n minus 3. Therefore, out of this recurrence relation, whatever I get for b n minus 1 will be simply equal to r. So, therefore, from this we will get r is equal to b n minus 1. R is equal to b n minus 1 by just comparing this particular term that we have with this one. Now, let us set b n. B n will be equal to a n minus p b n minus 1 minus q b n minus 2. I am setting n is equal to k is equal to n. So, that I have b n, a n here, b n minus 1, b n minus 2. Now, if you just look back into this particular coefficient, we have written s is equal to a n minus q b n minus 2. So, we have this a n, we have this particular both these terms we have. Therefore, I will take this to the left hand side and define this as my s. So, I can define s as b n plus b p b n minus 1. So, I will take to the left hand side and define this quantity s as a n minus q b n minus 2. We are going to write it as a synthetic division procedure. When the first step is complete, I am getting all my b k's using the values of the previous a k's. Now, after the first step is complete, I am able to therefore determine 2 quantities out of the 6 we want. R is determined immediately b n minus 1, s is determined as b n plus p b n minus 1. Now, I need the partial derivatives. Now, just as we have done in Berge-Vita, we will take this equation and differentiate it partially with respect to p and q and recognize them as the quantities which we can pick up from the next step of the synthetic division procedure. So, let us differentiate partially. So, let us say differentiate b k partially with respect to p and q. So, we shall differentiate b k partially with respect to p and q. So, I will have a derivative with respect to p. Now, a k is independent of p. So, there will be no contribution from here, there will be contribution from this product, it is a product of 2 terms. So, I will have minus b k minus 1 minus p partial derivative of b k minus 1 with respect to p that is the product of these two terms. Q is independent of P, so I will have only one term from here minus Q partial derivative of Bk minus 2 upon delta P. Similarly, differentiate with respect to Q. So, I will have partial derivative with respect to Q will be, now the contribution of Ak is 0, the P is independent of Q. So, I will have only one term from here, that is minus P partial derivative with respect to K minus 1 of Q, that is contribution from here. This is product of two terms. So, I will have two terms coming from here minus Bk minus 2 and the contribution is minus Q partial derivative of Bk minus 2 with Q. These are the two partial derivatives. Now, we want to show that I can write this exact form as we have done for B case. So, let us therefore write some notation. So, we will denote partial derivative of this with respect to P as minus Ck minus 1, Ck minus 1, that is k running from 1 to 3 n. It is just a notation. Now, let us insert it. If I insert it here, the we can see that there is a minus sign appearing both sides, there is a minus sign. Oh, okay, we will take one more step. Minus Ck minus 1 is minus Bk minus 1, this is plus P, this is Bk minus 1. So, put k is k minus 1 here, I will get here Ck minus 2 plus Q, this is Bk minus 2. So, I can set k is k minus 2. So, I will have k minus 3, or remove the minus sign, I can write k minus 1 is Bk minus 1 minus P Ck minus 2 minus Q Ck minus 3. Now, we shall suitably define these quantities that are occurring, we will put what is value of k. What I do, in order to show that this is same as the previous recurrence relation, let us write k is equal to k plus 1, replace k by k plus 1, then this will read Ck is Bk minus P Ck minus 1 minus Q Ck minus 2. Now, if we just go back and see what we had written for the coefficients B case, we can see that both of them are identically the same. See, Bk is equal to Ak minus P Bk minus 1 Q Bk minus 2. Now, I am replacing A by B and B by C, I get exactly the same thing. In other words, it would be possible for me to obtain the derivative with respect to P by using the synthetic division on Bk and get our Ck's from there. Now, we will recognize what the quantity is, but let us do for the second one also. Now, similarly, I would, to obtain the such a relation from this, I will now again denote the derivative with respect to Q. Partial derivative with respect to Bk by Q is equal to minus Ck minus 2. Remember, we are not equating anything, it is just a notation, there is no relationship, I mean we cannot combine these two. You say you are using the both, say put k is equal to k minus 1 here, are they equal? No, it is not so, because we are just using this as a notation so that I can bring this particular formula into suitable form. So, therefore, it is only a notation. Now, if I write this as minus Ck minus 2 here, I would get here minus Ck minus 2 on the left hand side. On the right hand side, let us start with minus Bk minus 2 middle term. So, let me write Bk minus 2, this middle term, then I will write this as plus P of Ck minus 3. Now, this is Bk minus 1 partial with respect to Q. So, I put k is equal to k minus 1, and similarly I will have Q Ck minus 4, this is k minus 2, therefore, put k minus 2 here, I will get Ck minus 4. Now let us remove the minus sign again both sides. So I can write Ck minus 2 is Bk minus 2 minus P Ck minus 3 minus Q Ck minus 4. Again let us replace k by k plus 2. So then it will read Ck is equal to Bk minus P Ck minus 1 minus Q Ck minus 2. This equation is identically the same as the equation that we had written in the previous step as this. Therefore, it is possible for me to get from the same synthetic division level to get the values of the partial with respect to Q also, except that we recognize correctly what are those coefficients that are obtained from there. If this is the common relation now, I will now take k is equal to 1 2 3 n minus 1, that is 1 less than the given polynomial, where I will define C of minus 1 which is undefined quantities starting them as 0, because you know as k is equal to 1 I will have here C1 B1 C0 and C minus 1, C minus 1 is 0. Now let us define what is C0. Now C0, if you put here k is equal to 1, I will here is partial with respect to Q B naught. So I will have here is partial derivative with respect to P of B naught. Let us just go 2 slides behind and let us just write down what is our B naught. B naught is equal to A naught. This is equal to B1. You are putting here the C naught, that is equal to partial derivative of B1 upon P. Now let us write down what is the value of B1. B1 is A1 minus PB naught. So I will now substitute this as A1 minus P times B naught. And this will be simply equal to the A1 is independent of P, this is 0, B0 is equal to A0, therefore its derivative is also 0. Therefore what is left out is the derivative of this product only is left out, and that is simply equal to oh sorry, I should put a minus sign, right, I should put a minus sign here. We are writing right through, that is equal to, let me just show you that. We are writing it this with a negative sign. So there is a negative sign there, this one, therefore this simply comes out to be B0. Therefore C0 is also equal to B0. Yes. Now from this we will now write down the remaining values of. Let us now I will just put this sheet once here. I need the derivative of r with respect to p, so I have to differentiate this with respect to partially with respect to p. So let us just retain it here. So what I will have here is I have to differentiate this with respect to p partially. So I will have here this. Now we can go to the definition of our setting this. Let us look at this definition. This is k is n minus 1, k is n minus 1 means minus c n minus 2. So the value of this is simply minus c n minus 2. Now let us also write down what is our derivative with respect to q. Now derivative with respect to q will be by this q, that is derivative of this one. Now let us go to the definition of this. This is your put k is n minus 1, I will get here C n minus 3. So, this value is minus C n minus 3. Then we need derivative of S with respect to P. Now, look at S here, S is B n plus P B n minus 1. So, we shall differentiate this quantity with respect to P. Now, let us differentiate it. This is B n pi delta P plus this is a product. So, I will have B n minus 1 plus P B n minus 1 by P. Now, let us again go to the definition of the derivative. So, let us first of all write this B n minus 1 first plus. Now, I want the derivative delta by delta P of B n. So, if you look at this, I have to set k is equal to n. So, this is minus C n minus 1. So, we will have here I should put a minus sign here, minus C n minus 1, and this is minus P C n minus 2. We have got this derivative here, delta B n minus 1 delta P is minus C n minus 2, that is minus C n minus 2. Now, I want the last one, that is derivative with respect to Q, that is derivative with respect to Q of B n plus P B n minus 1. Yes, it is a notation that we have used for the, we have denoted partial with respect to P as minus C k minus 1 and derived that these terms can be obtained from the single reconciliation C k, and C k is equal to B k minus that particular term. Then we have taken denote derivative with respect to Q as minus C k minus 2, and then we found that the recurrence relation is identically the same thing. That means, I will be able to get the derivative with respect to Q also, provided I use the correct definition of what I have started with. The definition I have started with is derivative of R with respect to Q is minus C k minus 2. Here derivative with respect to P is this notation we have used. So, from the same line of our synthetic division C 0, C 1, C 2, C 3, C n minus 2, by correctly recognizing them as the partial derivatives, I will be able to get the partial derivative with respect to Q as well as partial derivative with respect to P also. So, it is only the correct notation that we have to imply it. That is why when we are writing the derivative with respect to Q here, for example, derivative with respect to Q here, we are now looking into the definition of derivative of Q that we have used. Therefore, I am picking the correct coefficient that should be used in order to find the derivative with respect to Q. Therefore, this is how we are able to manage that all the partial derivatives will be obtained from the single line of synthetic division procedure that we have obtained over there. Now, here now I differentiate this and then substitute it. So, this will be simply equal to minus of, I will delta B n by delta Q, that is C n minus 2, I have got here in the previous step, I can use the same thing, and this is plus C n minus 3. Therefore, we are now in a position to get all the 6 coefficients from the single set of synthetic division procedure. These are 4 quantities that we have obtained, and in the previous step we obtained 2 quantities R and S here. R and S were coming from the first level of the synthetic division, and these 4 quantities are coming from the second step of the synthetic division procedure. Now, let us illustrate how the synthetic division procedure comes from here. Now, let us write down, as we have done in Berger-Vitta, let us write down, but before that maybe we should see what is the next approximation. Now, we are computing H 1. So, P 1 will be equal to P 0 plus H 1 and Q 1 will be equal to Q 0 plus H 2. So, we are substituting these 6 values in the earlier we have derived the values for H 1 and H 2, we will substitute in that and get the values as this. Now let us write down the coefficients a0, a1, a2, an minus 2, an minus 1 and an. Now if you unlike in the Berge-Vita, here we have got minus p minus q, the factor that we are multiplying with minus p minus q. So I will be performing the synthetic division with respect to minus p minus q. There we have taken it as p because all our positive multiplying factors are coming, but here we have got here negative sign. So we will insert it minus sign right over here. Then the whatever b0 is a0, that has been found, b0 is a0. Whatever the first value that is available, we are multiplying by p. So that comes from b1 is equal to b naught. So we can start, see, b1 is equal to a1 minus p b1. So whatever available value here is multiplied by this. So a0 is equal to b0. So let me replace it by b0. So I multiply this and this. So I will put it here minus pb0, and there is no previous value available for me to multiply by q. So there will be nothing here. So there will be nothing here. I add it, I will get here b1. I will get b1. Now b1 is multiplied by the current value, that is minus p b1, that is minus p b1. The previous value is available will be multiplied by q, that is minus q b0. Add it, I will get here b2. When I reach this position, bn minus 3 is available to me. So I will be multiplying bn minus 3 with minus p. The previous value is bn minus 4, that will be multiplied by this. So I will have minus q bn minus 4. Add it, I will simply get b3. Sorry, bn minus 2, bn minus 2, bn minus 2. So I multiply this by p minus pbn minus 2 minus qbn minus 3, I will get here bn minus 1, and finally minus pbn minus 1 minus qbn minus 2, and I will get here bn. Now the first level of synthetic division is complete. So I repeat now one more level of synthetic division. This is C0, C0 is equal to B0, we have proved C0 is B0, B0 is A0. So we will have simply C0. So the procedure is immediate. So I will have here, and this is C1, this is minus C1 minus Q C naught, that is equal to C2, and when we have come to bn minus 2, I have cn minus 3 available to me. So I will have minus p cn minus 3 minus q cn minus 4, that is cn minus 2. Then I will multiply p cn minus 2 minus q cn minus 3 gives me cn minus 1. Now the synthetic division is complete. Now these values shall now be used in the 6 quantities that we have obtained for R, S derivatives with respect to this. For example, we had written R is equal to bn minus 1. So the value, this value is simply equal to R, and we have also shown S is equal to bn plus pb n minus 1 n minus 1. So I add to this bn p times bn minus 1, that will be my value of S. There are other values that we have just now done it, that is partial derivative with respect to p is minus c n minus 2. So this coefficient, this particular coefficient c n minus 2 itself is derivative with respect to p. Similarly, we have shown the derivative with respect to q is simply minus c n minus 3. So this previous coefficient is simply derivative with respect to q. So similarly, we can obtain the remaining 2 coefficients with derivative with respect to p, that is equal to bn minus 1 minus cn minus 1 minus p c n minus 2, and finally derivative with respect to q is minus c n minus 2 plus p c n minus 3. Therefore, again to conclude, one synthetic division using the factors minus p minus q would give us all the 6 quantities that are required over here, and then we can obtain the values of H 1 and H 2, obtain the next iterated value P 1 Q 1, then we repeat the synthetic division with the P 1 Q 1 and then produce the next result. Now in the next class we shall be doing an example on this.